So we'll start. Okay. Again, let me quickly check what was there in the schedule for today. This anyway we won't be able to do today. We'll do tomorrow. We'll try to quickly finish this part off and go a bit into this. And yeah, okay. That way we are only half a day lagging. So now we will try to optimize the code we have written and try to parallelize it and see how much close we can go to the theoretical maximum estimates from the hardware that we have. So what I'll do is initially I'll just try to like get the speed up like to the maximum possible extent on my laptop, but my laptop has only how many few cores, and as we learned from the last session, cores is not the main bottleneck here. The bottleneck will be the number of memory channels and the speed of the memory DIMMs. So for the processors that I have, it supports only 2 memory channels and I have 2 DIMMs. So maximum I can parallelize my memory bandwidth limited code 2 times. Like it'll be 2x faster maximum if I use both the DIMMs simultaneously in a proper manner. So we will try to scale like that and then we'll go off to one big node. Is Metro available? We'll go to Rudra and scale there. Okay. Scaling will be a bit different. Okay, fine. We'll see what to do. So we have our code where we left it off. We have a timer set and we are printing a temperature. So last time we saw, we were trying to run with how much? We had built the code and we were running with 4,000 square. That was the size. And 4,000 square was giving, I think, 12 point something, right? Gbps, 12.5 seconds or something like that. So let's run quickly. And this is for 10 iterations. So it is 1.2 seconds per iteration. Yeah, 12.4. So, and the reference temperature is this. So now let's see if we can reduce the timings a bit. Before that, can we reduce the timings at all? Is this the theoretical maximum? That we need to know. So always before we time the code and try to optimize, first we need to know whether there is any scope at all of optimizing, or is this the best this hardware can do? So, by the way, I'm audible, right? Because I started talking and didn't check.
Yeah, yeah.
Yes.
Okay, sure. So we have, okay, let's look at the basic kernel or function that we are benchmarking here. So update function, as I said, init is called only once. There's nothing to optimize here, or even if there was, we won't care about it because it's called only once. So it's not a critical performance critical part anyway. So in this portion, we are doing essentially 2 things. We're looping over once here, looping over here once. Let's simplify things a bit. For this kernel, essentially what we are doing is, once this temp new is updated with the temp plus CFL into Laplacian, this business, we are just copying all the values back here, which is just a very redundant operation. Now, why is it redundant is that if we were to remove this, a lot of memory transfer operations will go away and our code will become faster. Now, why is that? The basic operation, which you can call a memory transfer operation, is something like this. You have array A, you have array B, and you're doing something like AI equals BI. So essentially, if you look at, again, the motherboard diagram that we had, that is the best place to go to. Yeah. Or let's go to a better diagram. Yeah, this is a nice diagram. So this gives you a schematic overview of the entire motherboard that is there in the Rudra. Similar things will be there in my laptop also, your laptop also, but in that case it will be only one, one processor and only 2 memory channels. Here you have 2 processors, and 8 channels per processor and so on. So essentially your data is stored here on the RAM, whatever array you have allocated. When you are doing a temp, okay, let's simplify this a bit more. Let's take a test code. Call this copy, copy.cpp. What we'll do is, copy.cpp is very simple. What it does is, we'll have a double array called A, dynamic array, A, and we'll initialize this with nx. And we'll have an array B, nx, double, sorry. I might be making typos in this session, so please let me know if you catch any typos immediately. And what we are doing is, for just one time step, or leave the time step part also, just for one time, we are looping over the entire array up to nx, and we are copying the value ai, okay, ax equals bx. Okay, let's do it this way only. And what we'll do is, for now we'll not use CMake. This is a simple enough code. Oh, genius. Let's put it outside. That will be easier. Sorry, GP. NX. Okay, that also will come across. This I should do this. Okay. And if we run copy with suppose 1,000 size array, oh, okay, it runs at least, but the main thing we have to do is we have to put time, otherwise what's the point? Chrono. And we'll just copy paste the chrono code that we got from the example. Reference.
Samdeep, is there any preferred thing for measuring time? Like you have TikTok and other things also.
Yeah,
all are all in the same ballpark, or is there?
Yeah. Well, nowadays, yeah. See, most of these timers will have a microsecond accuracy, at least, if not nanosecond. And nanosecond it won't be. Software level things have only microsecond. Okay, so yeah, you can use OMP W time or OMP time or MPI wall
time. They're all
time.
equivalent.
They're all equivalent. Yeah. Okay. So where, as long as your timings are on the order of 1 second, all are equivalent.
Right, obviously.
Okay, so we'll just compile this and run it once. Okay, it says stands for -5 seconds, so we'll increase our size of the array a bit, and maybe we'll, just for the sake of statistical analysis of and removing a lot of noise, we'll do this over some n samples. So let's call it s samples. So we'll do it over n samples. And then for each thing, samples also will keep as a command line argument. Okay, so you have your timer ready here, yeah. Elapsed time is this, and per sample, the total per sample elapsed time is this. Okay, there's a big thing, just let's store it. Auto is okay with everyone, no? Because auto tries to reduce the type automatically in C++ 11 onwards. So you don't have to remember what type it was. It usually doesn't have any effect on performance, so you can use it freely. So this is total time. It's elapsed seconds. This will be total time and it will be by n samples. This will be a real number divided by an integer. So the result in C++ will be a real number itself. Otherwise, you have had to do 1 into n samples and others. So we can. Sorry. What happened? Suddenly? Oh, 10 samples. Okay, good. So as you can see, at least the scaling is fine. Per sample, it is 10 per. Okay, this is going completely haywire. So that means it's a. There's a. Previously, when we ran with one sample, it gave me 10 to the power minus 5. Now with 10 samples, it gave me 10 to the power 7 to the power 7 10 to the power minus 5 and so on. So this, as you can see, this is very noisy because the time is so small. This clock software is not able to capture it properly. So what we'll do is we'll increase the size of the array a bit. Plus 1 KB or 8 KB as it is taking now, being a double of 8 bytes, 64 bits into 1000 elements, sit hard. It'll be sitting in L1 itself all the time, L1 cache. So we'll increase it to 1 million.
So basically, if the array is small, then
it will be allocated in RAM, but at the first iteration itself, it will be picked up and put in cache. So it will stay there. And cache has such a high bandwidth that it's hardly justifiable to try, measure the bandwidth inside L1 to L1 transfer.
Probably it'll be TBPS or something.
Yeah. So usually the jump depend nowadays in today's architectures, the jump is 3 to 4 times. So L3 will be 3 to 4 times more than RAM bandwidth. L2 will be 3 to 4 times more than L3.
L3 like that.
Yeah. Okay. So if we increase, so let's make it 10 million. So 10 million here. Okay. So per iteration is 0.2. Let us make it per iteration. We'll make it around 100 million. Now we are talking. Okay. So per iteration is 0.27. The question is this good enough? So let's do a theoretical calculation estimate first. As you can see, this is the main meat of the operation is here. AX into BX. So what is going on? Essentially, the A array, this one, and the B array, both of them have been allocated. If I'm allowed to use this, otherwise I can find the motherboard of my laptop itself and explain, but this is the same thing kind of thing. Just imagine one processor instead of two. So they have been allocated on the RAM. And every time I'm calling like A0 equals B0, it will go to that address where A0 is located. Pick up, first it will pick up B0 because it's going to read B0 and then place that value into A0. So it'll go read B0. So basically that B0 data will be fetched to the processor. And then it will be fetched to the processor in the sense that from the memory address, which you can get by doing something like, let's do that actually. What is B0? The address of B0 will be simply the pointer of the array. B plus 0 if you want. You can write it like that. And if you did something like this, it would be the actual value. We want the pointer. So if you compile, I hope it compiles. It doesn't require anything extra. Oh, it will run now. Okay, fine. Okay, so this is the memory address of that pointer location in the RAM. If you count these, this will turn out to be some 64 bits. With
Why did
six,
you do plus 0, man? Are there?
so you can do pointer arithmetic in multiple ways. So you can either do it like this.
Okay. Uh-huh.
Okay, this is like you choose the element array and then take the address of that.
Okay.
Or you can just, since it's a pointer anyway, you
Mm-hmm.
can just jump 0 elements away. So this is one element away, two
Okay.
element away, so address, huh?
Not used to it. Okay.
Yeah. So this is the address. And if you actually calculate this value, or if you look at the number of bits, let's do that actually. So this is a hexadecimal value, right? So let's do hexadecimal binary. So you'll see that there will be quite a few bits here. I don't know exactly how many, but essentially what will happen is if all the numbers are properly filled in, you'll find that there is 64 bits. It's actually not 64 bits here. It's less than that because the remaining bits are zeroed out. Essentially, on a 64-bit machine, your RAM address space, the total like theoretically available RAM address space is 64 bits. Like there can be 64 ones and zeros. That will correspond to a maximum of 2 to the power 64 minus 1, which comes to around 64 exabytes. Exabyte being 10 to the power 18 bytes. Okay, so that's a huge amount of RAM you can theoretically have. Now, out of that, the actual RAM which you can utilize, it depends on the hardware you bought. Obviously, you can't buy 64 exabytes of RAM. I don't think even the world's entire 64 exabytes of RAM is actually not that impossible anymore. I think Fugaku itself has 100 petabytes of RAM. So just add one more, you're at 1 exabyte. And yeah, okay. So it's not that.
Petabytes of RAM.
Yeah.
To
Actually, this is a Japanese supercomputer, Fugaku.
Oh, that.
Actually, it might be more. Wait, Fugaku's RAM is how much? See, we have a total of 130 terabyte, which is really low. Fugaku RAM. How much is it? It's showing per node. Of how much does Fugaku have? One is, okay, memory. This is terabytes, so 5 petabyte. Okay. Okay. So it has 5 petabytes of RAM, but this is not the best example because it is HBM. 5 petabytes of HBM is really something. Okay, so it's sorry, yeah. So basically, if you want an equivalent in terms of the normal DDR4, that would be around 100, yeah, or at least 5 times 25 petabyte of RAM. Okay, so theoretically, a 64-bit machine can address up to 64 exabytes of data. Out of that, you can actually practically utilize whatever hardware of RAM you have bought. In my case, it is 16 GB only, very humble. And so basically the OS will take some virtual address. This is a virtual address. So if you actually calculate, this will correspond to some huge number, 10 to the power 12 or 13 or something. So it will basically it will create, the OS itself will allocate memory at some offset, like 10 to the power suppose 13, it will start from, and then it will start incrementing 1 megabyte, 2 megabyte, and so on. So the actual value of, absolute value of this pointer address depends on the starting value, which is completely arbitrary, depends on the OS, and even keeps changing every time you restart. For example, when we talked about yesterday, about the position independent code, if you were actually compiling a position independent code, this is guaranteed to change every time. Okay. So if you are doing again, okay, so this is changing, but this can change accidentally also, depends on the OS actually. Yeah. Okay, so if you want to guarantee a change like that, okay, first of all, this is not a very good example of using position independent code, but roughly something like this happens. So as you can see, okay, one thing you can see, the OS loves this 7F offset. Essentially, it starts from there every time, and then you can calculate what this number is. That will be at least the meaningful bytes that you have. It will be within 16 to the power 12 or 16 to the power 9. Yeah, I think this, let's do that. This will correspond to a decimal number of bigger than that. Wow. Something. Okay. 10. Okay. 10 terabytes or something. Oh, sorry. This is not the correct way to measure it. These actually are not just in terms of bytes. I think these are in multiples of 4 bytes or something like that. Anyway, doesn't matter. So it keeps changing with an offset. So that is how the pointer address looks like in hexadecimal. We'll go back to our diagram. Where is it? Yeah, here. So B is somewhere located, and B0 you're calling in to the processor. The moment it goes into the processor, it will be taken into a register in the processor. So now, like we did yesterday, if you just drop in the assembly code of this, no? So G++ minus S copy CPP, it will generate the assembly code of this. So just go to copy.s. This is the full assembly and so on. The relevant portion, so it's so big because we have included all this Chrono and all this, which have a huge assembly signature. But the main relevant portion of this you will find in, actually it's very difficult to find just a small move when there are so many complicated functions here. You know what? This is where breaking it up into library comes in very handy. What we'll do is we'll just call something called the copy function. .cpp. This is just for temporary sake. I'm just to demonstrate. I'm not going to do anything fancy here. So let's call this void copy. And we are going to pass array A, array B. That's the idea. And the size also. Let's make it dynamic, nx. And we'll go from 0 to nx. We'll generate the auto file and the assembly corresponding to that. That way it is going to be very clean, no include errors. Oh, sorry. Nx, right?
Correct.
X equals px. So now we're going to do G++, generate the assembly of this small portion. We'll go to copy func.s. This also generated a bit more, but okay, still manageable. So as you can see, it says something. These are all metadata. Okay. The main portion of the code is basically here, and so on. So if you would like to read it in a more user-friendly way, Ravi, what are the flags that you use? And annotating the line numbers, annotating the source code. This only will do it, is it? Okay, so there's basically an option which actually shows you the source code line also along with this. Okay, fine. Just checking a small thing. As you can see, anyway, so I was talking to you, telling you about these, like this virus's crown sticking out. In your live auto files also, there will be this function signatures sticking out. These are those function signatures. So basically, if a auto file has, remember we did, what was our function signature here? Copy func.cpp. Copy double star nx. Huh. So this will copy the name here. Z4 is just starting this thing. And usually whatever the, so there are, depending on the particular type of signature that you're putting, it will keep changing. Here, for example, I think this is the part where it is copying from the, okay, yeah, I think this is the part, yeah. So, yeah. Which one? Oh, it's minus verbose ASM. Oh, okay. So where is the line number? Here. So you can see the inline source code that you have. So you can see that the for loop that you were writing is being unrolled and these many instructions are being generated. There's a reason for each of these lines. Why are they being broken down into multiple? Why are there multiple repetitions and all those things? The multiple repetitions are basically for if-else conditions. If my pointer address is a multiple of 8, I can do an optimized copy directly by cache line and so on. If it is not, then I can't do an optimized copy. I have to do some other kind of copy. Okay, so these 4 different versions of the simple AX equals BX is basically the compiler doing an if-else condition, because it doesn't know, like at runtime, what kind of a RAM you'll be allocating this memory on. Because you can take this executable and not run it on this laptop. You can take this executable compiled here and run it on some other machine. Fine, that is okay completely, as long as the libraries match up and all dependencies are met. So that's why optimized, like a compiled code or a binary, always contains all these if-else conditions that internally handles things. If it doesn't know.
So doesn't this increase the compiling time or affect the performance?
Compile time will increase because the compiler has to now generate a lot of if-else conditions and edge cases. Performance will not decrease.
Decrease, yeah.
Performance will not decrease that much because, as you can see, usually in our programming styles, we don't use this concept of go-to. There's a concept of go-to where you can.
Yeah.
Okay.
Yeah.
So you label a line number and then you jump directly to that go-to line number in the code. So here in assembly, go-to is used heavily. So these are the labels in assembly. And for example, when it says JGE L4, it basically means that whatever was the comparison operation here in the previous step, if the number is set, if the bit is 0 or 1 or equal to something, then jump to L4, else continue here. What is L4? L4 you'll find here.
Okay.
So it will jump here and so on.
L4 cache.
No. This is completely different. So this is just a label. I can even name it something else, like ABC1 or something, and correspondingly change the label here.
Okay, sir.
Okay.
Thanks.
Just a label. So okay. I think so now. Okay, if you really want to go into assembly, we can go into all these things. But just the one thing is that essentially what this move operation means is that it's taking a double word. Double word basically means, again, I think this is 64 bits or 8 bytes, right? Word is 4 bytes, right? Okay. So double word is 64 bits or 8 bytes, which is a double variable worth of stuff. It is taken from a pointer, RBP. So RBP is the origin pointer and -4 is the offset. As you can see here, it is offsetting. We leave the offset part. Okay, so from some pointer it is reading and putting into this register called EAX. EAX, EBX, and RDX and all these are small 64-bit registers that are present in the processors, like very near to the instruction where the actual computation happens. Okay, these registers are the fastest things in any computing hierarchy. Like it is faster than cache itself. Okay, so there are registers like this. So essentially, pointer memory address location is being read from the RAM, and it's coming through the memory bus and into the register like this. Then, okay, so this is exactly not B0. This is basically you're checking here. What you're comparing is X less than NX. So one of these values is NX, one is X, and you're comparing. And only if X is greater than NX, then it will go jump to 4. And exit, basically press a return value here. And if it is not less than, then we'll keep iterating. So it will not jump over to L4, it will keep continuing here. Here is the first instance of an actual pointer being, the B0 being used and transferred here. And then you'll see a move where from the pointer, something has been written back. So which one is that part? This is that part. So essentially the thing goes like this. From the right hand side, you're reading into the left hand side, into the register, and from the register somewhere, like for example, this is also a register. From here, you'll be writing back to the pointer. Again, basically back to RAM. Where's the exact version of this? If we have this, the complement of this writing back will be somewhere else. This one. Yeah. So no. So where is the writing back happening? This one, yeah, okay. So yeah. So this one is going to, okay, this is keyword means, yeah, okay, it's two double variables together. XMM, if you already have seen a bit of SIMD, is one of the SIMD registers of width 64 plus 64, 128 bits. We'll come to those XMM, YMM, ZMM if it is required. It's not required like desperately, but okay. Okay, this is basically how it is working. So essentially there is a transfer happening from the RAM to a register in CPU, and from that register in from EAX, it will copy to EBX register, and from EBX, it will transfer back to RAM at the location where A0 is. That is the basic idea of this function. So that is the basic idea. And then it will go to the next X and then pick up B1 and again read it, put it into a register, and from that register, update another register which should have contained the value of AX. Or it can just take the register, put B1 in the register, and from that register write back to this memory location in RAM. So this is how it goes back and forth. So essentially, in terms of memory or data movement operations between RAM and the processor through this memory bus, you are doing a one read and one write back. Okay, so that is how you count the number of memory operations that are going on. And how many memory operations will you be doing total here? So if there are nx variables, you'll be doing one read per variable, one write per variable, so 2nx memory operations. And what is the size of each data point? That is a double, so it's 8 bytes. So essentially you'll be doing 2 nx into 8 bytes, that is 16 nx bytes of data will be transferred in one loop of this. If that is the case and your memory bandwidth is supposed to be, then how much wall time should it take? It will take 16 nx divided by p seconds. That is the theoretical calculation. So let's do that for an actual case. How much is my memory bandwidth? If I go back to that, did we calculate? What should my memory bandwidth? Okay, let's quickly do it again, just to revise once. What is the processor? They have it open somewhere. Yeah. We have 34.1 Gbps, 2 memory channels, 2133 MTS. So this into 8 bytes into 2 will give you 34.1. That is the maximum operations that are possible, maximum memory bandwidth that is possible. If I'm utilizing this full memory bandwidth and I have, what is the size of my array? Oh, the NX that we were sending was this one. So 100 million, yeah, 100 million. Okay, and we are doing it 10 times. So okay, let's open up. What do you prefer, Excel sheet or notes? Coders. So we will do notes.md. Or if you want, you can actually write it in the documentation. There's a nice way to do things. Or better still, where we write usually is in the issue itself. We comment in the issues. That is, can we just close this out? It's here in itself as a theoretical estimate. So we'll start commenting here. Theoretical estimate for copy. So let's do this calculation. So the kernel is for int x ax equals bx. This is the kernel. So for a sample value of nx equals 10 to the power 8, I'm using 100 million. My laptop bandwidth is, as Intel says, or we calculate also, not Intel says, 31.4 gigabyte per second. Okay. And we have per variable, we have one read plus one write. So basically, there are two mem operations per variable. So for nx variables, it will be 2e8 mem ops per variable. ops for one loop of one loop kernel, and we are doing. Why are we putting everything in code? Sorry, this is not how it's supposed to be. Usually you put like, yeah. Nice. Okay, so 2 to the power 8, 2 into 10 to the power 8 memory operations for one loop, and we are doing it for 10 iterations. For 10 iterations, there will be 2e 8 into 10, which is equal to 2e9 memory operations. And if you want the GB of data being transferred, then just multiply by the type of the size of the each variable. So, which is equivalent to what? 2e9 into 8 bytes, because we are using double 64 bits, which is equal to 16 or 1.6 into 10. This many bytes, or essentially we are using around 16 GB of data being transferred through like 8 GB being read in the from the RAM to register on the processor, and 8 GB being written back. So now, is this calculation correct? Just let me know, because I might be making a lot of mistakes. If this is the GB being transferred, and if my bandwidth is that much, let's bring the bandwidth here. We'll be using it here. Yeah. This is the GB being transferred, and bandwidth is this. Then what should be the time taken? So time taken should be 16 GB divided by the memory bandwidth, which is 34.1 GB. PS is equal to how much? 16 by 34.1. 0.46 or 0.47 seconds. And what did we get? What's this for? Oh, no, it's okay. What did we get? Oh, we'll not run this. Did we run this case in particular? What were we running? We were running copy kernel, is it? In that thing? Sorry, there are too many. Let me just, so if that assembly thing is done, then just let me remove this copy kernel function. Huh? Or maybe when we need it, we'll write it back. Because it's on the fly small thing. There are too many. Okay, fine. We are doing that only. So I'll remove this memory dump also. So if we run this, 100 million. So 1, 2, 3, 1, 2, 3. Should be a better way of doing things. Well, we can put 1e 8 here itself, and it'll convert automatically, hopefully, but I don't know. Oh, what am I doing? Why am I? This is sad. Should have taken 0.47 seconds for 10 iterations. Instead, it took 2.6. So how much off are we? We are around. Just 1 minute. Yeah, we are around 2.64 divided by theoretical estimate is 0.47. 5.6 times, okay, which is bad, really bad. If you're 5.6 times slower than hardware theoretical limit, it means something needs to be done seriously, properly. Okay. First thing we can do is we can try to push the compiler a bit. That compiler, please try your best and give me a better code. You're not giving best code. Okay. The simplest way everyone knows is we have not been using the optimization flags. By default, compiler uses O0, which means no optimizations at all. So if you compile and run, we'll see you're getting 2.64 here. So let's see what, okay, that 2.64, 2.67, that is static fluctuation that we can leave. If you have so many browser tabs open, the fluctuation should be even more because the RAM gets keeping dynamically allocated and reallocated here and there. So if you go to level 1, let's see how much better it is. Is it better at all? A little better. Okay, 1.67. So we're down to 2.5 times. By the way, it doesn't seem right. It doesn't seem right. This, how is it even? Okay, we'll see. I'm a bit surprised that it is already 2.5 times only. Usually with G++ minus O0 or O1, you expect it to be 10 or 100 times slower. Okay, so I'm a bit surprised. Maybe my calculation somewhere is wrong. Can anyone verify or just redo the calculation quickly and say if it's okay?
Looks fine.
Looks fine. Okay. I'm surprised. Okay. ECC is doing really well then. Or my RAM has gotten the hang of it. It's trying to. Okay. So O2 decreases a bit more, but not as much as the jump that was there from O0 to O1. And finally, this is the latest. Usually compilers stop here. Minus O3 is the best optimizations in a deterministic way that they can do, like without breaking the mathematics of the underlying algorithms. If you use OFAST, there's a possibility it might be breaking some numerical calculations of overflow and all this. Won't be reproducible. Okay, nice. So using O3, we are able to come to 0.95. So what, as compared to 0.47, this is a theoretical estimate. I'm still surprised that this is the, because, okay, we'll come to why I'm surprised, but okay. So we are on around 2x away from the theoretical estimate, right? Twice the amount which we should get. Now, what did the compiler keep doing behind the scenes? If you really want to go into the details of this, I would suggest you again write that copy kernel. So I would say you take your small copy kernel from here, write a function out of it. So let me call it copy small or copy func. I shouldn't have repeated that. Okay. And forget the send samples for now. It's okay. Coding convention, this was supposed to be covered, we did not cover. We'll quickly do it later on. Two tabs, two spaces, no tabs. No, and especially not four spaces. You just call your G++ on this copy func, and you pass your optimization flag and ask it to generate assembly and MASMS Intel. Intel syntax doesn't matter, leave it. Minus F verbose, this will give you the source code inline in the file. So you can go to copy func.s and you can see what it is trying to do. It has a lot of these if-else conditions. Like it has different if-else conditions for different conditions on the locations and the memory addresses of AX, BX. As I was saying, is it integer multiple of some cache line number and all those things that you'll try to check. Okay. If you do O1, what is it trying to do? Let's save it by name. That way we can cross compare other assembly lines with this thing also. So S, let's remove it and we'll generate it as func ASM for O3, O1, O0. Okay. O1 and O2. I don't want, I'll just take a screenshot of the numbers so that we can get back to it later. Or if you want me, I can save it in a file so that we can do a small check later. If I save it, we'll put it here. And comment it as finished. It's stored forever. You don't have to go back and forth looking for files. If you look at copy func O0, first of all, how big is it? 106 minus all these business. So effectively, you can start from here, so 52, and you can end here. So roughly around 52 minus 79 minus 52, which is 27 around. On the other hand, if you look at O1, interestingly, it starts here, 54, and ends here almost 68. Huh? So you have 68 minus 54, which is 12. Okay, so from 21 it came out to 12. Here, these are all better. It's even smaller. It effectively starts. Okay, this you can leave for now. Actually, we should leave that. Actually, no, this is actually part of it. Let's start from here. This is also how much? 65. This is 12. Again, roughly 12, 13, something like that. So one thing you will notice is that this, in a particular section or the most crucial section which is being repeated multiple times, if the number of instructions or the number of lines in the assembly is small, it means it is guaranteed that your code will be faster. Actually, no, okay, that's a very wrong statement. It's not guaranteed that it will be faster. You also have to see how many cycles each instruction takes and so on. But assuming if all the instructions take the same cycle, which is not the case, but assuming that, if that is the case, then the number of lines basically tells you how fast your code will be. Okay, so that is one way of looking at it. The second is if you see that XMM, YMM, ZMM, these kind of things are being used frequently, it also indicates your code is actually getting auto-vectorized. So the compiler is trying to utilize the underlying SIMD concepts. So SIMD will come to a bit later. Okay, let's quickly get over with SIMD. If you have had some basic exposure to parallelism, which most of you have, but if anyone doesn't have, you can use multiple cores to distribute your jobs and do tasks in parallel to reduce the effective overall wall time. Right? Like you employ more workers to finish it off quickly in a distributed manner. If you had only one core, then you can't launch your job on multiple cores. Like it's a theorem. Okay. Instead, what you can do is Intel, AMD, and most modern processors come with this option where core itself can pipeline your underlying these assembly instructions in such a way that, or not pipeline actually, that's the wrong, that's a different concept altogether. If your compiler finds, or if you also understand that your code is written in such a way that multiple variables need to be processed in the same function or using the same function or instruction at the same time, there's a scope like that. What you can do is you can pack up those variables, like 1, 2, 3, 4 variables, into a small block and pass it to, under a special function called SIMD functions, where the SIMD function will operate on all the 4 blocks at the same time in one cycle or at one shot. So the simplest example is that if you have a simple add.cpp, if you had, okay, let's do copy only. That way we'll not lose track of things. So in copy func, you had this. Suppose your instruction was something like this. Copy is not A equals B. Oh, this can also be simplified. Let's do it more explicitly. AX equals BX plus CX. As you can see here, essentially what you're doing is, for every data point at AI, BI, and CI, or AX, BX, CX, you're doing the same operation. There is no difference between the operations that you're doing at A0, A10, A50, and so on. Okay. Effectively, what you can do then, or effectively, when you want to simplify the code, what SIMD would effectively do is, it will think of it like this. X0. Tell me if this code is equivalent to the code that you already put. Then keep the code as comment. Tell me if this code is equivalent to the previous code. Like, so version 1 and version 2. You think it is different? Why is it different? Or functionally, is it different or not? In the end, will AX contain the values that you would expect out of version 1 as well? If that is so, then essentially, if this is the kind of unrolling of loop that you can do, if that is possible, then you can, Intel and AMD compilers give you a special function instead of just this plus and equal to operator, wherein, see, timing wise, what a single code serial code would have done is, it would have first executed this line. So what would it have done? It would have gone to the RAM, gone to CX plus 0, this memory location, fetched the data, gone to this location, fetched the data into the registers E and BX, EBX, then added them up in the register itself using something called add EAX, EBX, and then from that like a resultant value which is stored in one of the registers, it would have written back into the RAM location here. Then it would have again gone and fetched the data from here and the data from here, again put them into the register, again written back to RAM, again and so on. It would have gone like this. Using SIMD, you can fetch all the four C values at one shot, all the four B values at one shot. You can do the addition of this vector, like this vertical vector of B vector and C vector at one shot, and then you can write at one shot this vector into the four locations simultaneously at one shot. Okay, so essentially, what would have been a 4 times sequential calculation or processing becomes just a one-step processing. Okay, so the way you do it is like I'll just show you briefly how it's done. There are specific the function names are a bit weird. That's why I don't want to get into the details of it. So essentially, okay, this is a version 2. This is the semi-simplified version or the loop unrolled version. This will also actually sometimes, if the compilers are not being able to understand this is simplifiable code, just if you unroll loops like this, no, it helps a bit sometimes. Again, you have to actually profile your code to see and see the assembly to see whether it's actually helping or not. Sometimes it helps. The version 3, which is a SIMD version, would look like this. Suppose this is double, right? So you will need to require, you will use a SIMD register which can pack in 4 doubles at a time. Usually that is called the YMM register, or if you want to program using that concept, it's called a MP. This is correct. Aryan, is this correct? If you're there, I don't know. So let me call this YMM C. YMM B. Okay, let's not do this. We'll do it step by step. YMMP is basically this horizontal vector version that we're going to pack these 4 versions. It's very simple. What you do is you say equals. This is again a function name which you get. Sorry, 256. By the way, oh sorry, I forgot to explain. 256 basically represents the 256 bits that you're going to pack. So if there are 4 doubles, each double is 64 bits. 4 of those become 256 bits. Right. So this is basically a 256-bit register. You're going to pack this into, and D stands for double. Because you can also have something like float or just like this, int I for int and so on. So we are going to pack doubles. That's what I'm telling them. So load PD. The precision double. I think this is not required here. Yeah, the P comes here in the function. If you really want to see where it is, all these functions are, you can go to intrinsics. I'm just quickly glossing over this SIMD part because only if it is needed, we'll do a separate optional session. Otherwise, no need for this. Why is error loading data? What Intel gave up, is it? Load PD. What happened? No. Intel intrinsics. Loading data. Interesting. What happens suddenly? Why is it behaving like this? It's down like this. It's very bad. Okay, fine. Basically, you can find it here. I don't know. The page is not working right now. Or can someone check if this? Ravi, can you check if this page is working? Okay, leave it here. Recording. Maybe someone broke a JavaScript somewhere. Wait. What is there? Failed to load. XML request core. No, what? Has been blocked course policy. Crap only. They changed their server or something. Okay, so 256 load PD will essentially load 4 doubles starting from a given pointer address that you give, which will be basically b or b plus x in this case, b plus x plus 0. Or if you want the actual pointer way of, like other way of doing pointer arithmetic, then it will be b of x plus 0. So basically, you load x0, x plus 0, x plus 1, x plus 2, x plus 3. This is the, so this takes care of the loading part. Now you load c also, like this. Then you add. So here you'll store the resultant in a, which is, again, you have to explicitly write an add function. That's why intrinsics look a bit dirty. YMMP, YMMC. And then you store it to the A. So you're storing it, just is that. So the function for that is M256 store. You're going to store to A this address of A plus 0, and we'll be storing which value? The YMMA value. Okay. So this is the simplified version of the same thing. This will be around 4 times, theoretically it should be 4 times faster than this one or this one. You'll get around 2.5, 3 times faster, depending on how much bottleneck your instruction cycles are, how much register, how many registers are left in your processor and all those things. Okay. So I won't compile this right now because if you really want to see it, you have to iterate over it at least 10 to the power 7, 8 times and then do it in a good, like I don't have, I have AVX2. So whether you have AVX2, this 256-bit wala assembly registers, you can just do LSCPU and check if you have something called AVX2 in these flags that are given here. So can I see this SSC, SSC2? These are also different types of SIMD things. These are 128-bit SIMD registers. So you can pack only 2 double at a time. So the maximum, theoretical maximum speed up you can get in terms of compute is only 2x on these registers. AVX2 is there. So I should be able to run that code. Maybe after some time we'll run that code and check if it's actually 4 times or 3 times and so on. So let's keep it aside for one. We'll call it did we name it? I forgot. Where did we even write it? Why is it not showing up here? Did we delete it? Oh, oh, add. Where did that go? That's very weird. Is it in research? Ah, no. Extremely weird. Where did that file go suddenly? Does anyone know? It was called. Oh, it was copy from the CP. Oh, okay, thanks. Oh, I just saw add.cpp and that's why I got confused. Okay. Okay, so we'll just store this as move to copy. Move this to SIMD add. We'll look at it later. So just going back to the optimizations. So here you can see that XMM is one of the SSE type of registers. Huh? So 2 doubles can be stored inside this. So what it is trying to do is it is trying to pack 2 doubles. Like RSI is again a 64-bit register, which means it can carry 1 double. It is trying to pack 2 doubles into this register for some reason. It's trying to do some optimization somewhere and so on. So if you think about it for some time, you'll try to understand what this Bichara compiler is trying to do and help you. So this is how it tries to optimize. The basic point is, so if you really want to go into proper performance optimization, the first thing is you can try to learn a bit of this SIMD, a bit of these assembly instructions. If you are able to learn assembly instructions, you actually don't need a compiler because you will write your assembly code directly. The compiler's entire job, or not entire, like the main job of the compiler or an optimizing compiler is to generate an optimized set of assembly instructions for the very bad high-level C++ code that you write. Okay. Now, instead of writing C++, if you're able to write assembly itself, then instead of writing this loop here, you can replace this with something called an inline assembly. So instead of this part, you can call, again, Ravi, what is the syntax or something? It's called inline something, MSM. Roughly looks like this. So you can put in registers here like EAX equals E, move. You put those assembly here itself. C++ accepts inline assembly. So something you can do. And if you do that, there is nothing for the compiler to compile assembly or generate assembly code for. You have already given the assembly code. So if you learn how to write an assembly, you don't need an Intel compiler, you don't need an AMD compiler, just any normal simple compiler will do because you will be the compiler yourself.
Sir, I had one doubt.
Yeah.
Sir, there are also the way we explicitly give the data type like n double or whatever it is. We can even explicitly give it register data type. So what are that? Does that speed up to some variables if we assign register A, register B, something like that? In CPP.
In CPP. So how
Yeah.
would you do it? Like, what would you call it? Like, what is this register class or
Auto register, I guess. I do not remember exactly, but
auto register.
Yeah.
See, this register, no,
So I
people
read
don't use.
somewhere
Yeah,
that
yeah.
it is fast.
Well, it's a hint. It's sort of like that inline thing. Huh. It's a hint to the compiler. It doesn't guarantee anything.
Okay.
If you really want to take full control of the code and the performance, it's best to what do you say? Best to code directly in assembly. But assembly is a bit tricky because you have to take care of a lot of edge cases and so on. Because one edge case you miss and some weird offset of pointers come, code will give second file. And debugging assembly is hell.
Yeah, and also that is like you said, like that is best way of doing it. But there also could one write inefficient way, right?
Oh
Assembly.
yes, definitely. Yeah. Inefficient assembly is the number one cause of slow codes in legacy codes because some person came in very excited. Oh, I'm going to write direct assembly. They wrote assembly, but not the first assembly. Actually, it was worse than any simple compiler would generate. Yeah, it will slow down your code much more than a normal. So basically, okay, I would say that you use the normal compilers that are there only if you think, and if you're seeing a bottleneck somewhere. Sorry, there is a train that will go around now. Yeah, only if you see a very bad bottlenecked portion and you are not able to restructure the code or the data structure, all the algorithm, like keeping the algorithm the same, just restructure the variables and for loops and so on in a way such that the compiler is able to understand. Then you can just generate the assembly of only that portion of the code, because most probably if you're writing a library, you'll have all these small functions in separate CPP files. So you can generate the assembly of only that CPP file and see if it is trying to do the best possible thing. If not, then you can think of trying to do a hand modification of the assembly and put it in. So the first step is obviously compiler nowadays, because most compilers they have, like the compiler engineers, they have had what, 30 years of experience now as an industry, compiler industry, more than that, but I'm saying the really Intel and AMD and all these things. They know most of the design patterns that come and what the best optimizations for them will be and so on. Here and there will be few cases which require some special attention that you can ask their developer forum and they talk to them and they. So for example, we keep pointing out assembly changes, more optimizations that can be done to Intel and AMD compiler teams. So and they're very happy. They like to receive feedback like that. Okay. So yeah, so basically the idea is to put as much knowledge into the compiler itself so that you don't have to write assembly yourself and so on. So then minus O2 is again smaller or almost the same size as O1, and O3 is finally this much. Oh, O3 is very large. The only thing is, although it looks very large, you'll see that most probably the most oft repeated portion is actually very small in terms of instructions. So I guess that would be this portion itself, yeah. Or it's at least equivalent to A2, O2 or something. You can see it from the time stepping times. Yeah. So 1.3 and 0.95. Anyway, basically, if you really want to see what with how this is exactly taking 0.95 from these instructions. Each of these instructions have a corresponding, these are opcodes, and they usually have, for your given processor's architecture, there will be a data sheet which will contain how many cycles it takes. Okay, so if you look at Intel x86 add, sorry, 64 add cycle. How many cycles? Okay, we can quickly go here. 4 cycles. So one cycle for each add. Okay, like this. Or if you can go to Agner Fox instruction tables, they also have some things summarized. But I don't know if it's for x86, the modern ones. Do they have? Oh, they have till 11. Nice. Okay. So yeah, you can, if you really want to do a hand calculation, you can, this look like those, log tables which we used to see in school. I used to hate those things. So I usually don't go into this level, because if so much you will do, then what will Intel do? Let them do something. Okay, then leave it. Let's get back to the timings now. So we were able to, the compiler was able to give us 0.95. So then we are almost 2x away from the theoretical bandwidth. So how can we make up for this 2x? As you can see from this the spec of my core, my processor cores, it says that it is 34 Gbps, from which we calculated that 0.47 thing. Okay. It says it is 34 Gbps for 2 memory channels. You can utilize 2 memory channels simultaneously. Okay, simultaneously is the word. You can utilize 2 memory channels simultaneously only if 2 cores are running independently, almost independently, and accessing data in parallel from the 2 memory channels. So essentially, you have to use 2 cores. Okay, in the sense, or in other words, you have to make your program multi-core or multi-threaded or multi-process. Okay, this is the introduction to parallelization. So basically right now what is happening is, if you look at the diagram, which we had, where is it? There are 8 RAM, okay, in my case, imagine there's 1 processor and only 2 RAM sticks. This is the scenario in my laptop. Currently, A, B might be sitting in 1 RAM, or suppose A was too big and it took up the entire RAM and B was pushed up to the other RAM. But since we are using a single core only, the core will first fetch data of A and then put in data of B. Like this, serial it will keep doing. If we start using 2 cores now, then what it can do is, one core will anyway fetch from 1 RAM. The other core can also fetch data from the other RAM. So basically, the memory controller that controls the data flow between the RAM and processor, that can actually pipeline this data transfer. That I know that core 1 and core 2 both want data from this RAM. So I'll pipeline it properly. And if that happens, then the latency comes down and you'll effectively be picking up not that much. Well, actually, pipelining won't double your thing. It will maybe increase a little bit. The main thing that will happen is, let me show you the example once. So if a core is reading from one particular RAM stick, no, the other core, although the memory controller can pipeline a little bit, it won't make the data transfer rate double, because there is a hardware limit to it. It can't suddenly double things if the channel has a certain limit. So ideally, you should not allow 2 cores to access the same RAM. One core should access one RAM, the other core should access the other RAM. How do you ensure this? Okay. Just before I go into this, let me clarify what I said in a bit more detail. So just give me, I want to show you how it looks inside a AMD processor, because that I think is the best. Just 1 minute. Yeah, this one. to show you how it looks inside the processor. So this is how the core layout is inside AMD's one processor. Similar things can be shown for Intel's processors also, but Intel's is a bit messy. That's why it's called the mesh architecture of Intel. This is called chiplet architecture because you can see each core is like a chiplet chip kind of thing. Okay, so these blue dots are cores. So this particular processor, which is the green package or socket, that has how many cores? So you have 4, 4, 8, 16, and this thing. So 32 cores. Each group of 4 cores share a L3 cache. Okay. And 2 such groups share this, what do you say? This orange box, which is called a NUMA node. We'll come to what is NUMA node, forget about it. So basically what it says is 8 cores like this are sharing 2 memory channels. Essentially these vertical lines that you're seeing going out, they will go to 2 RAM slots or 2 RAM sticks. So basically 8 cores will end up drawing data from 2 RAM sticks. In Rudra, it's a bit different in the sense that L3 cache is shared by 8 cores instead of 4. So instead of 4 cores here, you can imagine 8 cores in this package. So 16 cores will be sharing 2 memory channels. That means 8 cores will be sharing 1 memory channel. So the division is like that. So if you quickly want me to draw it in a way where you can keep a reference, because this will become important when you try to optimize your codes on the cluster. Or actually, you can do the same thing for any AMD processor, not just the cluster one. If you try to do this same thing for Intel, it will fail a bit because Intel doesn't respect this kind of a simple logic. Intel is a bit complicated. Okay. So this is suppose my bunch of cores. Okay, we'll draw cores in a rounded fashion like AMD does. So this is my core. I have how many cores? So basically I have, or maybe it will be there online. If you search for AMD 7742 layout, maybe it will be there, but let me quickly give it to you like this. Okay. So it's not like this exactly, but roughly it will look like this. So this is one block. Maybe one more block like this. And there will be a small, there will be RAM sticks coming out. So there will be a RAM stick, just 1 minute. This is one block, huh? This is not a one processor. This is called a NUMA node. I'll tell what the NUMA node means. So there will be one RAM like this. Let's make it green because usually RAM DIMMs are green in color. Okay. And this is one. So, and the channel, memory channel, basically comes from this box into this one. So if you really want to thicken it a bit, this is the memory channel. Okay. So basically all these 8 cores are able to access this memory channel almost at the same speed. Okay. This distance is not representative of the slowness or something. It's just, yeah. So similarly, you have NUMA node is basically, it runs for non-uniform memory access. It basically means that if I now copy this and make it 4 of these, this is how the Rudra's 7742 processor looks like. Is there an invert operation where you can just flip it? Rotate, huh? Flip vertically. Nice. Oh, it's too big, but okay, anyway, you get the point. So this is how the Rudra's processor looks like. So you have 8, 8, 16, 16, 32, 64. 64 cores per processor. And there are 8 memory channels, 4 up, 4 down. Okay. And Rudra itself is made out of 2 of these processors. So you'll have one more sitting here.
So what is the name of this memory hierarchy? So 16 cores, is it called a block or node? What is it called?
16 cores is called a NUMA node. A NUMA node
NUMA
is
node,
NUMA basically means non-uniform memory
Memory
access.
access.
What basically it means is that these cores can access the the data from these RAMs decently fast. Okay, so basically, some access like this will almost be the same as access from here to here.
Okay.
But if I am trying to process data on this core and trying to access the data from this RAM, it will have to travel a long distance. Okay, and there will be a lot of latency, and the effective bandwidth of such a data transfer will be very low. Okay, so NUMA nodes basically group cores which can share or which represent a group of cores which are able to share data from their corresponding RAM slots almost at the same rate.
Okay, and so the 16 cores share the same memory. So are they working on shared memory? Wala funda. Is the memory shared between the 16 nodes equally?
Okay. See, any memory or all the 16, any memory that you allocate on the 16 GB of RAM, that will be shared or visible to all the 64 cores in this process, in this node. Okay. So that is the funda of the motherboard, that your whatever is there on the motherboard is visible to all cores. At what rate, that is different, because that depends on the distance of the core from the RAM stick and all those. But in principle, yes, each core can see a data in any of these RAMs. So in that sense, all data allocated on this 512 GB of total RAM as we calculated is visible to each and every core in this node. If there is data allocated on another node, there is no physical connection between the two motherboards. Well, the direct connection, indirect connection is there through interconnects and Ethernet cables and all those things. But direct connection is not there. So that data in another node is not visible. So this is the funda of NUMA nodes, and this is how NUMA nodes are. Like NUMA nodes are not that important a concept. Also, I don't know why people keep harping on that. It becomes important if you want to fine tune at a certain level, but okay, it's not that great. These are the RAM and channels and things like this. Okay, so just going back, this HPC performance. Where is that? Yeah. The HPC performance guide. This is for a older generation of or a lower generation of processors where AMD ships with only 32 cores instead of 64 cores per processor, but this funda is the same. Okay. Now let's go back to our actual thing. Oh God, we are going to shoot across no MP and OpenMP. Just optimization is happening now. But we will try to figure out quickly. So coming back to this point of the diagram, we were trying to see how to reach that theoretical estimate of 0.47. Right now we are at 0.95, right? So we have to essentially we have to distribute this task of this function, or the simpler one. Where is the simpler one? Copy func. Oh, copy func becomes mdadd. Okay, fine. We'll do copy only. We have to basically distribute this task into 2 cores. How do you do that? The simplest way to do it is, we'll do OpenMP quickly. Just, I think most people know OpenMP. Just in case you don't know, just stop me wherever you feel it is going too fast. The simplest way to do OpenMP across 2 cores, if you know you're going to use only 2 cores, is just put #pragma OMP parallel. This basically creates a region where multiple threads will be spawned. To each thread, you give some task. I will basically divide the array into half and half, left half and right half. So this will be n by 2, and this will be it. And this is not exactly how you do it, but there's one more step here. So essentially what we'll do do is we'll generate this parallel region. We'll spawn two threads. So num threads will be two. This is the worst way of doing OpenMP, but as a starting point, this is fine. The standard libraries, as we discussed, third-party libraries go on top of standard libraries. So include omp.h. So here, what you're doing is you're going to generate a parallel region where you will spawn two threads right here at this bracket, and you want to give this job to one thread and this job to the other thread. So what you'll do is OpenMP gives you this function called OMP get num thread. It's the ID of the thread essentially. Okay. The thread, if my thread number is 0, then I'll do this. If my thread number is 1, I'll do that. It assumes you're hard coding for two regions, two threads. Huh? Okay. So that's it. This is OpenMP. And you have parallelized your code also. So I'm not missing anything, right? Because this, if I try to simplify too much, sometimes I do something very, very wrong. And you have to pass a flag OpenMP. All compilers, mostly all compilers come with OpenMP inbuilt in it. G++ OpenMP copy.cpp. And we'll be passing how many? What was the thing we were passing? Per each. 1, 2, 3, 10. Again, same mistake I'm doing. Okay, we'll do it.
It's lagging a bit, Samiti, the screen.
Is the video stuck or is it just for me?
Yeah, I think it's stuck, I guess.
Yeah.
Okay. Wait, I'll rejoin. Okay.
Yeah.
At the best part, it's stuck. Oh, God. Yeah, my network is a bit slow. It's even taking time to load the entry screen. Am I still audible?
Yeah, you are audible, but yeah, there is a.
But yeah, let's see.
lag.
Yeah, there's a bit of lag in my voice also, is it?
No.
No, not lag. I mean,
Okay.
in between,
Oh,
like, will.
crack.
Yeah.
Okay. Yeah, I think the network is a bit slow now. I don't know why. Maybe this GeoFiber people are laying cable near my house or something. They'll dug up everything around my house. So again, do a synchronization check. A, B, C, D, E, up. Okay. Or lagging?
Yeah. It's okay. I think.
Oh, there's a lag, is it?
Yeah.
No, wait, then I'll close my browser because, okay, wait, just 1 minute. Because this part is important. If this is done, then most parallelization stuff is done. Yeah, it should be fine now, I hope. Let's see. A, B, C, D, E.
Yeah.
Yeah, it's better.
So what we did was we basically created a parallel region where we put brackets. So essentially it looks like this if you really want to see that without the pragma business. Sorry. And then we put a pragma, which basically means whatever is in this region will be executed by all threads. How many threads? We have generated 2 threads for this region. But we don't want both the threads to update both the arrays. So what we have said is thread 1 will update the left half of the array, thread right. Otherwise, if the thread array is 1, it will update the right half of the array. That's how you split the task between the two. So now let's actually run it and verify
Yeah, I
whether
think we lost you.
again.
No. I think Maro,
No.
your internet. It's clear for me. I don't know others, but
Okay.
yeah, I think
it's clear.
Maro, your internet.
Okay.
Oh, my internet problem, I think.
Yeah.
Sorry.
Oh, my power went off. Maybe that's why my network lagged a bit. Okay. So yeah, we'll compile this code. What with this copy.cpp. And now, okay, dot out. Okay. Right out. 100, 1, 2, 3, 1, 2, 3. Then let's see how much it takes. It took 1.02 seconds instead of, oh, sorry. It actually increased decreased the performance, like increased the wall time a bit, right? So what was the timing that we got previously without just any of these business? 0.95. So it increased a little bit. So why did it not half it? Let's look at it once. So one thing is,
So what are we measuring right now? Wall time or user time?
this code gives you the actual wall time.
Okay.
If you are referring to the user time which comes from here, oh, sorry. Here you will see that the user time is almost double of the real wall time
Yeah.
because
2 threads.
2 threads. Yeah. Or like yeah, it's not exactly double, but something. Actually, this gives you an idea of what might be going on. Does anyone have any suggestions? What might be going on? For example, I suppose I am at a wit's end as to what is going on. It should have worked. It should have half the time. We have decreased the number of operations. First of all, let us see. Okay, with one.
Still going serially, no, in this.
Well, you're spawning 2 threads here,
2 threads, but
and then you're giving thread 1 to this and thread 2 to this,
okay.
and it's half and half. So let's do one thing. Let's verify. Let's debug OpenMP. I haven't done that since 2012. Let's do one thread first. This code will work. It will just should take half the time. Okay, because forget half the time. Let's just do it full. Let's see how much overhead we get out of this only. Introducing OpenMP gave me overheads. And basically, OpenMP is bad then. Okay. It gave me 1.277, which means there is an overhead. The overhead is usually there because you are trying to spawn threads, which is a bit of time-consuming operation. If I just remove this pragma business, and this also, and this also, like make it a normal serial code, this comment or so that I can quickly come back to it. Give me the previous performance, right? Let's just verify that. Otherwise, something might have changed in my RAM allocation also. It's giving me 0.97, which is sort of the performance we got earlier. So the baseline performance is fine. So the question now is, what am I doing? Time. Let's remove this time. But as you can see, this is more accurate. This is a bit, this is a sum of system time and user time and all those things. So leave that. So this thing. The first thing that we should check is where is the memory getting allocated at all. The fun thing about C++ or nowadays any OS based memory allocation is Memory does not get actually allocated when you do double mu. Memory gets allocated when you first initialize it. Okay. So it all depends on where you're first initializing it. That is one thing. Here it is actually happening fine, but just this is one thing usually. So essentially, this will be even worse, or maybe not in my laptop, but generally this is worse. If I suppose initialize all the values to some arbitrary thing, A is 1.5 and B is 2.5. If I did this, let's run it and check once. Oh, this is serial anyway, it won't matter much. If I did again, parallelization like this with 2 is 10, 5. Actually, you know what? It's best not to try this on my laptop because now I realized why the problem is. This is not a very good example of showing OpenMP scaling. Let me shift to Rudra. Huh? That will be much better. The same code I'll call because the problem is one of my.
Samiti,
Yeah.
in that code,
Yeah.
you had written pragma, this one, right? OpenMP. There should it be outside the samples too, because every time it will spawn in some sense.
The thing is, if you put it outside,
Oh,
it will try to parallelize the samples loop.
Okay.
Yeah. Okay. So the reason I'm saying this is because if you run a benchmark code here on my laptop, it will not scale also because one of my teams is a bit clunky. Okay, to get it to repair in NASA's shop. So let me go to a proper machine where you actually see scaling. So let me go to Rudra. Rudra, we have like tested through and through. So this will scale. So let's copy this to Rudra. So SCP copy. And the second thing is it's not optimized for Intel. JCC does not optimize very well for Intel. So we'll go to AMD and use AMD only. Go to Rudra. Anything else that we might need? We don't as of now. Okay, go into Rudra and do it. As before, I will drop into interactive node. I'm sorry, I'm going a bit over time. Just give me 10 more minutes and I'll wrap this up. At least OpenMP will be done then. So, oh, what are all these things? Oh, God, sorry. So we have copy.cpp here. And what we'll do is we'll compile this with, let's say, AMD compiler because we are on an AMD architecture. Okay. So what we'll do is we'll do module load. Let's use MP5. Otherwise, if you have not used AMD before, there are a few changes that need to be made to make it optimal. So ICC or ICPC for C++ minus O3. And you're doing OpenMP, if OpenMP or QOpenMP also works. And then you will have, what do you call it? The file name itself. Okay. This does not by default put C++11. Now, if I run 1, 2, 3, 2, 3, 10. By the way, now we actually get to redo the calculations because the timing says, let's just run and see how much it takes. Okay, 0.554. How much this should actually take? Let's do the calculation once for Rudra. So we'll just copy paste this whole thing. and try to see how much it should actually take. So we have 10 to the power 8, this is fine. The bandwidth of the entire Rudra cluster, okay, bandwidth per channel, I would do first. Huh? Bandwidth per channel, as we calculated, was, you remember, from the AMD site, we did those calculations. 446. Let's go to 7742, that is R. So it says that the MTS is 3.2 gigahertz, like billion transfers, DDR4, and 8 channels. So let's do it for one channel first, and then we'll do it for two channels because we're going to run a two-channel code, because we're going to use two memory channels only, two cores. And what is the memory bandwidth for per channel? That is 8 into this 3.2 G. So that would be 8 into 3.2, 25.6. So I'll just note it down. I'll just note it down here. Per channel is 25.6. Yeah. And if it is two channel, it will be double of this. So actually, let's not edit it. Okay. 26. And two channel bandwidth will be double of this. So 51.2. And then the time taken for one case should be, so let's break it up like this. Huh? Time taken for one thread should be, if I was doing the whole thing, then it would be 16 GB of data with 256, 25.6. And that would roughly be 16 divided by 25.6. So 0.625 seconds. And if I did it with 2, then it would be 2 channel memory bandwidth, and time taken for again 16 GB would be 51.2, which is divided by this only. So, so I erased my calculation. 0.31. Okay. So let's see now actually how much time it takes. So we'll just erase this. This is from my laptop. So we ran with 2 and we got 0.459, right? If we run with 1, how much do we get? So with 1, we'll just comment out that other portion. Actually, yeah, this is the other portion anyway won't come because there will be only one thread. So the thread ID will always be 0. So let's compile it again. So it says that I am getting for one channel case this much. What was my estimate? 0.625. I am getting 0.79, which is not bad, but it's not the best. Huh? And there's a reason behind that. So let's just note down the timings once. So for my actual run, actual wall times. So one channel case is this much, and two channel case, or two core or two thread case. Huh? Because you don't know whether you're actually using two channels. You only know for sure you're using two threads. Wait, why is it? Oh, sorry, I'm copying the wrong value. How is it faster than theoretical? It's like more than the speed of light kind of stuff. Okay, so as you can see, the scaling is not that great. First of all, second, it's a bit off. We were expecting this much for one channel, this much for two channel. It's a bit off. So why is this happening? This is where we need to analyze the code a bit more. We are not far away, but a little bit more is remaining. You really want to go as close as possible. The first thing is, as I was saying, nowadays in most modern compilers, memory is not allocated in the RAM when you actually do a malloc or new or something like that. It gets, or even a static array. When you define, first create a static array, that is not when the memory gets allocated in the RAM. It gets allocated only when you put the first value into any element or in particular portion of the elements. So this is where it will actually get allocated, the memory, not here. So if you do a free, so this is suppose one stage, this is like stage 1 and stage 2. So these are regions. If I do a check of free minus G at stage 2, no, you'll still see that it's your RAM is not occupied. It's like using the same ambient baseline RAM usage that is there, that is still there. Only after this, if you do a free G minus G, you'll see that this whatever GB of RAM, whatever it comes to, this 10,000 something, that is being allocated. Okay. So, and where is this being allocated? That is the next question. As I said, each core, remember the diagram. Quickly pull up the diagram. Each core has its own specific favorite RAM to go to in terms of distance. So these cores will prefer this RAM, these cores will prefer this RAM. Although this cores might, in case of overflow, prefer this RAM also. There won't be much of a penalty. But this core definitely won't prefer this RAM. So it's like that, no one knows. So usually when you do this allocation or initialization, AX equals 1.5, for A0, or like whatever this code is handling. So here we are in a serial code, so it will be the main code itself. So the first only code which is running right here. This code will try to allocate the RAM, this whole array, whichever RAM is nearest to it. So suppose this main code happened, the OS decided, okay, this code I will run on this particular code. So it will allocate on this RAM, not this RAM, not this RAM, and so on. Okay. Now, what I'm doing is, I'm trying to generate in a parallel region. Sorry, this should be, let me generate the parallel region again. So I'm going to generate 2 threads here and distribute the task. If I'm going to distribute the tasks or the left-hand side of the array and right-hand side of the array like this, but if the OS decides that when I'm doing this thread splitting or creating 2 child threads, the one thread will stay on the mother process or like the original parent process that is there. The other thread can actually, so it all depends on the compiler actually, where it, if you leave it to the compiler, by the way, it depends on the compiler, only if you leave it to the compiler, that one thread might be running on this core, one thread might actually go out to this core. Okay. Then essentially what would happen is, if the original core was this one and the entire array was allocated on this RAM, and now during the MP region splitting, it has, the first thread is in here, but the second thread has gone here, then it will have to fetch data from this distance and it will slow things down. Okay. So what you do is, whenever you parallelize stuff, always ensure that you follow the same parallelization pattern in the initialization also, because that will decide the pattern in which the memory is also allocated. So ideally, what we would do is, we would put a parallel here also, so that it initializes also in a parallel manner. Usually all these topics don't come in OpenMP directly, but OpenMP is actually a very cute way of showcasing. This is called the first touch policy, the initialize alloc on initialization. And that is what most compilers do. So basically, if you're getting seg fault and you're thinking that, or it's because of memory overflow, just check if you're first initialized at all or not. Because if you're getting a seg fault even before initialization, it means the seg fault is coming from something else, not because of memory overflow or memory misallocation and so on. Because the memory actually has not even been allocated. Okay, so So now let's see if that helps. The only thing is, see, these are two separate parallel regions. There is as such no explicit connection between these two parallel regions. Huh? So what the OS, again, if you leave it up to the OS might decide, okay, fine. For this parallel region, I'll put the threads here and here. And for the next parallel region, I'll put the threads here and here. Okay. Again, this whole parallel initialization won't help you at all because you'll be fetching data from here and there and here and there. So let's just quickly run it. Let's see if there is an improvement. Then we'll see how to take control from the OS into our own hands. Okay. In the end, basically, if you know the hardware, it is best to take all control in your own hand and the OS shouldn't interfere in your logic, things like that. Okay. Let's see. Point 4. Which is very weird because it says it's faster than. No, it's not faster. It's actually very nice, right? It became quite nice. So the OS is playing very nicely with us today. But still, it might not tomorrow. So the way you take control over which cores you choose for which parallel. Oh, sorry. Where am I going? So the way you take explicit control over which cores you choose for pinning which thread is this whole business of pinning. Now, how do you do pinning? So basically what I want is, I will generate two threads. I want to explicitly pin one thread here and one thread to the last one. This is my choice. Okay, I want to do it like this. How can you do it? Like I can choose to pin 10 threads in 10 different locations also. In a general way, how do you pin threads, OpenMP threads to cores? OpenMP gives you a set of directives or pragmas to do this. Let me quickly. Okay, let's do it. The first thing you can do is, actually this is, I really want to do it. Like the usual syntax I use is not going to help here for arbitrary locations. I usually pin to very uniform processes. So let me quickly check up the OpenMP pin to core list. So it will be OMP list or proc list or something like that. It will be, I just want the syntax. Ravi, do you have that list? It was this Nachiket gave us, no? That syntax. Okay, we'll search it. OMP proc list should be here. This is not going to help much. Okay, maybe the references will help. Oh. Proc list. Just give me a minute. This is really long. Nitya likes to go into details when she gives a talk. That's why she has so much. Do any of you remember Nitya coming to JNC and giving a talk in college building? Austin was also there in 2018, I think.
Oh yeah, I remember that name, Austin.
Yeah. So this is how you export OMP places. Let's try. I think this is an older OpenMP syntax, but just let's quickly check. Export. First, we'll do OMP display environment. No, what is it? Display MP. Display. All the syntax I'm forgetting nowadays. Here. So this will at least tell you how it is pinned. You'll be able to see explicitly. Then Tuck. Okay, then let's use this. Where is it? Export OMP places. One thing is bind. The first thing you do is let's do that. Second step. OMP places is. I don't think the syntax will work, but let's check. Because last time I tried with this, it was not working. But okay, maybe it will work now. It says some weird thing. Okay. Instead, let me not do that first and last. Okay, I'll figure out what the exact syntax is. And see, this is the problem. Sometimes they use brackets, sometimes they don't. That is the confusing part. Sometimes they will put explicitly. Okay, let's try explicitly also. Zero and core 64, suppose. Okay, or 63, the same. Okay, nice. So as you can see, when I pin to core 0 would be this, core 63 would be this. Okay, it becomes 0.51. Now suppose I choose, okay, again, I'm not very sure whether it's pinning to the exact same things, but we can check later on. There is a tool I'll give you, which we have written to exactly find out where pinning is going on. But let's see the other one. 0.24, which is a very weird number because this is not how it's supposed to be. Because it is using a numthread 16. Did we not specify it to use not numthread 16? This is the problem with numthreads, specifying numthreads here. So usually with okay, now is a good time to say this. Usually it's best not to hardcode the number of threads inside the code itself, because depending on the core machine you're running on, you can have access to 100 cores, 200 cores, and so on. So why do you want to hard code that you have to run with 2 only? So if you make the codes flexible, then you have to write a big if else condition like this: if 0, if 1, if 2, and so on. Instead of trying to do that, OpenMP gives you a very handy way of doing this splitting of the for loop over a number of threads. Instead of doing a OMP parallel for like this, instead of a if else condition, what you do is you just take your entire array, and you just add a pragma OMP for here. You already have threads spawning in the parallel region. Those threads will basically be taken up at this pragma, and they will be assigned in a nice balanced way to distribute the task over this entire loop. Or if you want even a shorter syntax, OpenMP allows you that also. This will be essentially you collapse all of these things and call it OMP parallel for. Okay. So these are the stages of OMP complexity or simplicity.
Sir, I doubt how does it do it internally? Like for जब लगाते pragma OMP parallel for.
Whenever you're writing a pragma, internally the compiler will be generating something called POSIX threads.
Achha.
Okay. POSIX threads are basically multi-threading facilities that almost every processor nowadays has, unless it's very, I don't know if ARM has or not, but it's Intel and AMD processors have. Okay.
POSIX is only Linux, is it? Or is it only Linux?
It depends on the implementation. GCC, for example, uses POSIX threads. If you look at the C++ library itself, it will have its own internal implementation of something, pthreads or something like that. Well, that is also POSIX threads. You're talking about you mean what is the threading in Windows and things like that?
Yeah. It will be the
Okay.
same.
Well, the concept-wise, it will be the same. It will call something else.
Yeah. So, but it might happen now that same memory means how is the synchronization taken into consideration internally?
Synchronization between what?
So same threads are accessing same memory location, so overwriting problems and all these things.
Okay, we'll come to that. Right now, whenever we are at a location X, it is only accessing the data for the location X itself in the two arrays. So it's not like location thread number X will be accessing the data for X plus 1, right? So that problem is not, okay, if you're saying that maybe one of the cores is so fast it finishes up all its threads work and then starts to take up other people's work and then it clashes with the other threads, is it?
Yeah.
No,
So
those are all done by OS actually. Okay.
oh, okay. So
So
that
all
problem
these
doesn't
threads,
come.
if you have this kind of a clean partition of the data where you have told that when I am parallelizing over X, which is the task distribution index essentially, and I am going to make sure that a thread at X is going to access data only labeled for X and not, this would create a huge problem. This will create a conflict. Okay.
Yeah.
This will not.
Okay. Okay. So got it.
You can bypass conflicts like this also by taking a bit more control over the way threads operate, but we'll come to that a bit later. So this is the syntax for hash pragma OMP parallel for. Similarly, you can do this for here also. So you go here, you make it the full thread instead of splitting it by hand by yourself. And you could have put a hash pragma OMP4 here, or if you wanted a single line, then you put this line also here. OMP parallel 4. Okay. So now let's compile. We were trying to see. Okay, yeah, we were trying to see whether changing the locations changes speed at all. And then we found out that it's actually internally using 16 threads. And then we wanted to get rid of that hard coding. Now, since you have removed the number of threads internally, how do you externally then specify how many threads to use? So what you do is we will, okay, let's first compile the code. Not DCC, what was we using? Okay. Now the way you specify the number of threads to use is OMP non-threads equals 1. And then you do another export, which is OMP places. Okay, in this case, you want to, let's do 0 first. And the second thing that you do is, during the course of the run, it is possible that OS might think that one core is doing a lot of processing and that's why it's heating up a lot, generating a lot of heat, and might melt the core also. Okay. So it might decide to, on the fly, during the run itself, change the location of a thread from, suppose it was running for the first 15 minutes on this core, next 15 minutes it might go put in this core. Although it tries to minimize this kind of a huge gap, it can do it. Okay. But again, then you'll have a problem that if this core was initially allocating data here, if it suddenly goes to this core over the runtime, then suddenly after some 15 minutes, you'll see your performance has dropped. Why? Because your thread migrated and is now going back and forth between a huge distance. So what you say is, over the runtime, you should pin my process to the same core throughout the run. Export OMP processor bind to true. Okay. So let's now run it then again. Now you see OMP threads 1. And for one process, I'm still getting a bit higher. This is a bit funny thing. This is because the array size is a bit large. This is splitting. Actually, the array size is a bit small. That's why it's fitting inside cache. AMD has giant caches. That's why we increase the size a bit. We'll come to that. Where's our repo? So basically, this smaller time that you're seeing, no, that is not exactly the theoretical time that we are getting. We are actually utilizing a lot of L3 cache bandwidth, which is 3 times or 4 times higher than the RAM bandwidth. So we'll take it out of L3 cache a bit. Just 1 minute. So when we saw that it is 10 to the power 8, basically it means it is around how many? 10 to the power 8 would be 8 into 10 to the power 8, so 800 MB. Okay, no, it's okay. 500 MB is total L3 cache, so we'll see how to do it. So this is good enough. Right. So let's now parallel extrude OMP places 0 and 1. And OMP diameter is 2. Parallelize, run. It's a bit, but not that much. It was 0.48 for one, 0.40 for another, for two cases. That is not at all scaling. Why? Because 0 and 1 belong to the same memory channel. So it's not being able to fetch data from the memory in a parallelized way. Okay. Ideally, what we should do is, if we place one thing here, we can place the other thread here or here or here, and so on. It's basically separate out. Give each of the threads its own memory channel. Huh? Okay. So we'll do that. The way you can do that is, the simplest short line command is, instead of places, you say course, and you say OMP prop bind spread. So it will try to spread out the things as far as possible. So if one is here, then the other one will be maybe here or here, like few iterations away, or few cores away, and so on. So let's again try. We're experimenting a lot nowadays, but okay, let's try. Okay, nice. See, so much increase happened just by changing the location. We are still using two cores. We are not using more than that. Just we change the location of the cores. So let's do it manually instead of doing it by a spread, because spread will just try to uniformly spread the threads as much as possible. So again, we'll go back to the places. OMP nonsense is 2. Empty places we'll come back to. So what would be, one is 0, one we would say 63. Basically, as far enough kind of thing. It's again decreasing. Okay. So why is that happening? We'll come back to it. Even I don't know it's happening like that. Let's say 16. See, you know what? I don't think this is the correct syntax. That's why it's not picking it up properly. It's saying this is fine, but it's not. Check what the exact syntax is. We'll go to AMD itself. Just 1 minute. This is one way of doing it. We'll try this. What is task set? Okay, let's try this. So essentially what it's saying is that I have thread numbers 0 to 127 with a gap of 8. Essentially then it will generate how many, like it will space out threads for every 8th core, right? So essentially it will have 16 threads with 8 cores space between two. So what we will say is, we will use 2 threads. We'll space out by suppose 16. So 2 into 6 is 32. So 0 to 31 will be our affinity thing. And we'll leave this OMP places business. We'll put 2 threads. Let's try. Nice. Okay. Now let's try with what is the actual diagram. Let's see. 8 and then 8. So 8. 2 into 8 is 16, so 15. So core, this basically means that if there are core IDs, ID0, ID1, ID2 up to ID15, attach the first thread to core ID0, then skip 8, and then you'll land in core ID0 plus 8, so core ID8. Attach the other one to ID8, like this. So basically gaps of 8. We are putting gaps of 8 because we know a group of 8 cores accesses the same memory channel. So if we keep the gap less than 8, then threads will end up accessing the same memory channel and there won't be any parallelization. So, yeah, this is fine. it again increased a bit. So the question is, why is this happening like this? Any suggestions? Just let me check one small thing. Or, yeah. Let me try an actual latency benchmark. We'll quickly check this. By the way, how much is this supposed to be actually? 3.1. It's taking lower than that. Okay. So that means something is off. If you really want to do a benchmark, no, we'll just take the actual HPC copy. Stream. Just stream.c is everyone's favorite copy code. You basically, whatever we wrote as copy, there's this basic thing that we wrote here. Stream is basically a little nicer way of writing things. A little more professional way of writing things. So this is called stream benchmark. This is used everywhere across the world to benchmark clusters. And we'll just quickly run this and figure out what is going wrong. We can try it on our code, but I just want to confirm once on this. So it's a big code and so on with a lot of things, except the basic kernel is basically this copy operation itself. So we will just compile the same way we were compiling previously. CPC. Oh, well, this is IC code, so ICC. There's no need for SVC++ 11. And this is stream. Okay, now does it tell you why it might be giving me some weird number? There are some flags missing. Okay. So this says I am getting only 43 Gbps. What was the, so this is basically Mbps bandwidth that you get for the copy kernel. So this is like a copy kernel, there's a scale kernel and so on. So 43 Gbps is or 43,000 Mbps is what you're getting. What are we supposed to get actually for two channels? 51. Okay. So this basically tells you that even on the industry standardized benchmark, we are not getting the full bandwidth. And this is usually the case with both AMD and Intel. Usually you get only 85 to 80 to 85% of the publicized hardware bandwidth. If you want the full blown, like as we calculated for one particular process, for one process of this processor, you'll get 204.8 Gbps bandwidth. Since we have two sockets of these, it should be 409 Gbps. If you run stream in its full glory on this node, let's see how much we actually get. So we will end up getting, to do that, I'll need to add a few compiler flags quickly. We should have added these to our codes also to optimize it a bit more, but just for, let me be. What else? AVX. Just quickly check. Oh. What else? This is MR, no? And ICC, so that's what I guess. OMP num threads. There are 16 memory channels here, so we will run with all the 16 populated. And how do you space it? So you can use OMP proc point, this one, equals, this is spread, OMP this is this course. Ideally, stream gives you 350 Gbps maximum. Still giving. Why is it giving this thing only? 41? That is weird. I think this array size is too small. Wait, what did we compile? We compile. What did you say? Gopen what? No, this is good. So good. We have the benchmarks here. I'm missing out. It's so late. My brain is shutting up. I'm missing something very, very silly. Some flag only something. Let's see. Stream. So many issues are there with stream, performance. Where is it? On Intel CPU Skylake, where is that fit? Oh, we were using this, huh? Task set. Don't want to use task set right now. Okay, fine. We'll just use this for now. Just confirm once. Otherwise, it'll be a huge embarrassment in front of a recorded session that too. Sad. Oh, now it's doing it properly. Let it run a bit. We'll give. It's okay. It's a bit large, this array. That's why it's taking a bit of time. Maybe we should give a large array. No? This is a bit too large. Too much time. Not good. How much is it? Oh my god. It'll crash the node right now. It's almost, I did intention to fill up the entire node. Now please stop. You saw how much it is? It's written here. It's 424 GB. We have 512. So, so let's 40 GB is good enough for me. Nice. So here you can see it's giving 346 Gbps. So what we'll do is we'll just follow the same style. So one thing is we will increase the array size so that it doesn't keep conflicting with L3 cache. It stays fully in the RAM and then gets prefetched to cache. And we'll tag things like this. Although this is not needed per se because I'll give you a tool which will show you exactly how to pin things. This is just to get your flavor of the scaling part. Or we can actually use this code itself. Let's use this code only for scaling purposes. So this is the full-blown bandwidth that you get. Note that this is 346 Gbps and the theoretical hardware estimates are 204.8 plus 204.8 for two processors. So 410, 346, that is around 85%. How much is it? So that much gap will be there in any practical server that you have. So if you go anywhere in the world, any AMD cluster that you run, this is the maximum you will get on AMD ROM processors, this family, AMD EPYC 7XXX processors. Okay. So for 346 by 410. Yeah, 85% bandwidth you'll get. So whatever you see here, little bit of, because it won't match up to the exact hardware theoretical limit. It's always, since this is the best and standardized benchmark for memory bandwidth that you have on for any kind of systems, people usually measure performance, memory bandwidth performance, with respect to stream itself. So they don't measure performance based on the hardware bandwidth. Or if you measure with respect to hardware bandwidth, just make sure to take into account that 85% discounting. Okay. So when people say we are performing at a theoretical best, it basically means compared to stream bandwidth, not the hardware bandwidth, because there's no software can achieve actually. this, yes, a good written well-written software will be able to come close to 99% of this bandwidth effectively. So now, if we just go back to our previous estimates, you can see how we will redo this part. So previously we were estimating it to be the theoretical bandwidths. Now we can just replace it with 85% of that. So it will push up the speeds a bit. And if you take the one node case, for example, here, suppose I give a one node run. Huh? So I say 0.1, here task set, I put it at node 0. Sorry. It'll take 10 times more, no? Or 16 times more time. Let's kill it. Let's make the array size a bit smaller. Okay, so here you can see each channel is giving you 35 Gbps. Okay, for one channel. That is a bit extra because if you just multiply this with 16, it won't be that linear. This will be more than 400 itself. So basically now if you start scaling with 0 and then 2 threads, then 3 threads and so on, you will see that usually the memory bandwidth that you're effectively getting saturates, and finally with 16 or how many ever number of memory channels you have, that will come and saturate to the maximum number that you usually get, which is on Rudra 400 and what was that? 346 Gbps. Okay. So this is memory bandwidth, the software accessible memory bandwidth instead of the theoretical hardware one. Similarly, for flops also, if you have seen cluster benchmarks, all the supercomputing cluster benchmarks, you will always see there is a number called Rmax and Rpeak. That also refers to the same kind of thing. There is a hardware-based, flop-based, or clock-based theoretical flops that these people advertise, and then there's an effective value. So I'm forgetting which one is which. Our peak, I think, is the actual practically achievable flops on a cluster, and R max is the theoretical limit. So here it's like memory bandwidth max and bandwidth peak. So bandwidth peak here is 346 Gbps. Okay. Now we can go back to our code quickly and see how badly or how well it was failing initially. So we have a simple parallel for given here, and we will compile it with the same flags that we used here. So just all these have certain meanings. We won't go into the details of these right now. It's not needed per se. If you want details, it's okay. There's another option. Let's leave it. No need. It's too much. Already we are past 1 hour late. So combine. What happened? Oh, sorry. This is C++ code. So ICPC minus STP C++11. So now we have this. Now we will run it with the same options that we used here. This is okay. Thread num is 1, and we will do a task set. So string, we will have our copy, which is basically here out right now. And we'll go to the array size, which is, I think in this case was big enough. We will put 100 on GB. 1, 2, 3, 1, 2. Oh, sorry, 10 iterations. Nice. So it says it takes 0.9, whereas it was supposed to take around 0.6 theoretically. So 85% of that more would have been how much? (625) divided by 0.85, 0.73. So instead of 0.73, we're getting 0.91. And if we use 16 cores, that's there now. Sorry. The full-blown thing, we're getting 0.46, which is very weird. So let's take in this code somewhere. These are not the numbers which should be coming. Okay, fine. What we'll do is we'll leave this here for now because clearly my brain is not working. Okay. But roughly this is how you parallelize codes. And if you want to have a go at it, you can write a sample code using hash pragma OMP parallel for and run it on Rudra, see if you are getting the scaling or not. And if you're not getting the scaling, then tomorrow we'll discuss what can be the possible issues. Because there are some issues in this code, which right now I'm too tired to identify quickly. Or if anyone else can, please let me know. Otherwise,
Sir, could you put barrier and check if that works?
Barrier where?
I'm not after that initialization wala loop.
Barriers make sense only when you are inside a parallel region. So,
Means I'm not sure. I'm just suggesting.
no, barriers won't help here. But there's nothing, no place we can put barriers actually. But if you put a barrier inside this, then you'll basically throttle the entire parallelization.
No, above that auto start wala thing.
But that is not, so here or here?
Sir, I had one question before this. So, जो पहला pragma है, उसमें threads बन गए, तो दूसरे pragma में अलग threads बनेंगे या वही threads use?
That is a good question. That is, well, it is separate, it is different, there is no guarantee. That is actually a possibility. But if you see, usually if you pin the like offsets like this, no? It is sort of guaranteed that the same sequence will be maintained. So even though effectively there are new threads, they will try to, so whatever the core one, whichever thread went to core one here, that same ID of thread will also go to the same core here also, if you start doing this pinning business and so on. Okay. If it is not explicitly pinned using all these kind of things, it will not, it can migrate and so on. So yes, that can be a source of performance loss. But in this case, since we are explicitly pinning, that won't be an issue.
Okay, sir.
Okay. Yeah, so we'll do this. You can have a go at it on Rudra, or actually on any of the machines, NIS machines and so on, if you want. Before that, I just want to show you how actually pinning looks like in its glorious form. If you go to systems and just download this repo. And there's a tool here called OM.
You're inside Node, no?
Yeah. So now we can go back. So you can go into systems, go into this MPI OpenMP proc map. This one basically gives you an overview of or a nice graphical representation of what pinning looks like with a hybrid of MPI and OpenMP. So if I just go to submit, I do the submit script, but what I'll do is I'll compile directly here. So let's use mpitch for once. So I will load mpitch. I haven't done OpenMP, MPI, so I shouldn't use mpitch. Let's do just OpenMP. we do MPI, come to MPI. So we will just do these three things. Export OMP num threads. Oh, sorry, we'll compile first. This will compile with the system default G++ compiler, which is what? GCC 4.8, very old, but okay. It's not MPI, so MPI is not required. So okay. Okay, if I do MPI, then don't do MPI, this won't work. So let's fine. For now, just ignore the MPI commands. Those are anyway not required. I've just written the code with MPI, that's why we load MPI. And then we will just use OpenMP. So one is number of threads. We will export that later on. Close. And we will use pinning to course. And then we will see how it looks like, a map of it. So OMP, anything else we need? And does not need that. Okay, that's it. Export OMP num threads. Let's say we want to spawn 4 threads. How does it look like then? Proc map. Let's go. This is how it would look like. So if I just reduce this font size a bit, or let me increase it, it's fine. All these dots are basically slots or ports in the system. If you count, there are from this bracket to this bracket, this is one processor. From this bracket to this bracket, there's another processor. So there's 64 such dots in this one, 64 such dots in this one. If I use this syntax of OMP places course and OMP proc point close, it basically means that there will be 4 OMP threads generated. G is the global thread ID, L is the local thread ID to each rank. So you can look at this line, for example. It means that the 4 threads will be spawned on processes or cores close to each other. Instead, if I use something called spread with OMP, it will spread the things far apart. So here you can see thread 0 is on core 1, the first core, thread 1 is on this other core, and so on. It's uniformly placed across all the 128 cores. Similarly, so basically now you can start playing around with all these kind of examples. Actually, this is a good place to actually check whether Nitya's syntax is correct or not. This is what I was going to cover. So let's take that. Yeah, export OMP places. 0. We will do this and we'll see if we are actually getting pinning on 0, 1, 2, 3 cores. No, I see. It is like this. So we will quickly try to figure out a correct reference for the, this is correct. Okay, nice. Okay, it will keep jumbling the order of the threads, but that is okay. That is not an issue. So this is correct, this one. Syntax. So using this syntax, can we try out our sample codes? In the meantime, overnight, I will try to figure out why this is not working. This is very embarrassing. This is a very simple code. This should work. I don't know why OpenMP is giving up on me today. Where is the code? Oh, it's not in there. Okay. So if you want, you can play around with this